Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Data Contributions to a Conversational AI Platform. And before we begin, I'd like to briefly review the format for today's event. This will be an hour long. We have two presenters who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, because we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speakers, Pavin and Lynn Armstrong with Voicebox Technologies. Now, Pavin is Director of Data Platform and Services at Voicebox. Previously, he was president at Conversational, a speech technology startup, and Director of Program Management at Atigio, a big data pioneer in healthcare. He holds a PhD in computer science from the University of Southern California, specializing in computational neuroscience. And he also did postdoc research at the Argonne National Laboratory. Now, Lynn is a data architect with Voicebox, having joined there in 2001 as one of the company's first employees. She developed many of the company's core intent determination algorithms, its initial server platform, and scalable cloud services for speech recognition and speech synthesis, yielding several important patents along the way. Now, Lynn is a native Alaskan, an avid ice hockey player. She holds a bachelor's degree in computer science from the University of Redland. So, Pavin, Lynn, hey, thanks for being with us today. We're looking forward to your presentation.
Thank you.
Now, voice technology and natural language recognition is at the forefront of AI development that's transforming our everyday life and will undoubtedly be part of our future. Deep learning is at the core of identifying and processing voice for automation and new innovations. So in today's webinar, Conversational AI pioneer Voicebox will share their journey from an on-premises system that was manually intensive and costly to maintain to an agile cloud platform that's allowed them to build, schedule, and run multiple production data pipelines that feed into their deep learning models with ease. So today we'll cover the challenges they faced with a highly complex legacy system, how they chose their final technology configuration, how they configured their system to allow them to process data much faster and more reliably, how they worked with their existing technology stack, including Elasticsearch, Redshift, and S3, and lessons learned from their data analytics journey. So Pavin, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. And good morning, everybody. My name is Pavin Kadena. I'm the director of the data team at Voicebox. And I'd also like to introduce Lynn Armstrong, who's our data architect. And we'll be going through some of the details of the general speech that I'll give. I want to start by talking about the fact that there's a data team at Voicebox, and we are going to cover some of the technologies that we use. We have a conversational AI platform, which is a multi-tenant platform capable of secure, performance, scalable AI conversations. And this platform is improved through our data contributions due to a process called continuous improvement process, which consists of a pipeline of services, tools, human labeling, and reports that enable a CAP to improve its performance over time. Today we'll talk about entity extraction, or what we call criteria development for things like POI, music, sports, stocks, etc. We'll talk about how we crowdsource for transcriptions and annotations, and I'll give you a walkthrough of the process of crowdsourcing and accuracy computation. So what we'll see in this presentation are, for my part, I'll be giving some explanatory slides to kind of give you an idea of what is entailed in creating a conversational AI platform and extracting data from it. And then Lynn will walk you through some notebooks and give you some analytic reports on counts and accuracy. What I want to mention also is that this is not a demo. This is actually a system in production. And because of our sensitivity to our customers' privacy requirements, there'll be lots of reports that will show without access and with some blurring. So as I mentioned, I'm the director of the team. We have 6 developers on the team. The technologies that we use include Spark using Databricks, which we use for distributed compute, Redshift, which we use for data warehousing, S3, which is also an AWS log storage account. We use SQL Server for some legacy computations. There's a platform called Cloudflower that we use for crowdsourcing. We use Power BI for visualization and reporting. And we've developed some internal tools, including Semanto, which we'll explain in a second. The way things worked before Databricks was that we would cut and paste from websites, or we would contract with data providers, and we would create a on-premise single store for our criteria. Now that's quite changed. We use scrapers, crawlers, and data partners, and we put the results in S3 and Redshift. We have several of these, so we multiplied this by however many entity extractions we want to compute. And we do a lot of transformations inside of Databricks, so things like aliasing, acronym expansion, numerical expansion, symbol to words, Unicode to ASCII, and many, many other things that we do inside of the Databricks platform. Before, maintenance was, was quite tribal, and we would suffer every time there was a team attrition and we didn't have sufficient documentation. Now, using the Spark notebooks that are available through Databricks Unified Analytics Platform, we're able to write all of these things in Python and Scala, and we have much improved documentation. Scalability was quite difficult before. We needed to write these very complex SQL statements and transform those into custom XML. And now we do all of that inside of Databricks, and it's parallelized by design. Precision recall was something that we struggled with before. It was very manual and required a lot of developer effort. Now that's all done inside of the Databricks platform. We use canonicals like Google, for example, for precision, and we use the logs that we gather for recall. We would need to schedule our frequency of gathering data manually before. Now that's all done thanks to Databricks using their automatic job scheduler. And data provenance was also an issue, where we got data, when we got data, and now that's all much easier with much easier traceability. I want to explain this diagram to you. The main interaction takes place between a device and our cloud platform, and each utterance that's exchanged between the two, there's logs that are created inside of an Elasticsearch, and we are able to extract, transform, and load those logs inside of the Databricks platform. We interact with metadata such as audio metadata, and we also have our tool Semanto inside there, which I'll explain in a second. Transcriptions take place on the Crowdflower platform, and we do annotations using Semanto. And those are re-expressed into our warehouse by way of which we can also do some reporting. And that same information is given to our NLU service and our ASR service in order for those services to be improved, and we redeploy that back into our cloud. I also want to express some thoughts about how our continuous improvement process works. At the very top there, you see the customer voice interaction, which leaves a log each time there's an utterance that's exchanged, and we extract those, we transform those, we put the recordings in S3, and we deal with the metadata, and at that point we're able to do transcriptions, which we do with an external crowd, and then we do semantic annotation, which I'll explain here in a second as well, using our tool Semanto. We're at that point able to do some reporting. All of our semantic annotations and transcriptions have to achieve a certain level of inter-rater agreement. And new criteria comes in all the time. Let's say, for example, there's music, there's new artists and new songs that are entering into the lexicon. We validate that data. We're able to do some reporting and monitoring at that point. And then we feed that data into our ASR and NLU models, at which point we do some regression analysis to make sure that there's only improvement. And then we're ready to deploy, and the cycle continues. I want to talk a little bit about our entity extraction, or what we call criteria pipelines. So we start with some data that's highly volatile data. For example, with music, as I explained, there's new artists and songs and albums all the time. And we need to acquire the data from reliable sources. So for example, for music, we use Discogs, which we download, and we scrape the Billboard charts. The pipeline needs to include the periodic data collection as well as versioning of the data. If we are gathering data from different sources, as we are in this case, we need to reconcile them to make sure that they represent the same data. We do a number of transformations and normalizations as needed, and we validate the data. So how does that work inside of our platform? We do all of this inside of the Voicebox data platform. I'm showing you a visual here, which at the top has the web server or file server. We extract the data, we put it in S3, and then we do some ETL on that notebook. The ETL can be best described by this chart, which is each time we acquire a new piece of data, we have to make sure that it's new, that it's not something that exists in our data already. We pull that data in, and because there's aliasing, we have to make sure that that alias is not re-expressed somewhere else in our database. So for example, Frank Sinatra is known by many aliases like The Voice or The Voice of Life or Chairman of the Board and so on, but they all refer to the same artist. A lesser-known artist like Roberto Luis Rivera, who's a DJ, may also have lots of different aliases, so we have to express those in our database as well. And once we do, that information is in our database, and then we proceed from there. I want to make a statement about transcriptions and annotations. Transcriptions are how you hear things, or where the ASR, automatic speech recognition module, operates. Transcriptions are very complex when you're talking about an in-car scenario. When you're in a doctor's office and transcribing something, or when you're reading a book, it's a very different scenario. In cars, you have noise. You have intermittent noise, like signal noise or honking. You may have clipped audio because people will sometimes speak before it's their turn to speak. You may have unintelligible speech. Somebody may press the button and, there's just chit-chat going back and forth in the car. You may have foreign languages. Spelling variance can be an issue. So, for example, the word John can be spelled John or Jon, and you don't really know which one is the correct one. Speaker volume issues may cause issues. So somebody speaks very loudly or very softly, or when they separate each word. That's not how speech recognition systems work. There could be baby noise or pet noise in the background. It's too expensive to gather this information externally, so we use it's too expensive to use it in-house, so we use an external crowd for that. And the important thing is that there is no Oracle transcriber. There is no one person in the world who transcribes everything perfectly. So the best that we can hope for is high inter-rater agreement. So 3 out of 3 or 4 out of 5 is the system that we use. Annotations are all about how well you understood the thing that was said. In our current methodology, we have an agent. So let's say weather or point of interest or music or something like that. There's a context which says where you are in the conversation. So if you, for example, you say call someone, the next question may be, well, call them on what? On their mobile or on their home phone. And then there is also the command, which, for example, you could be asking about the weather locally, or you could ask about a forecast in another city. And there's also the criteria or the entity extraction component, which talks about, if you're talking about Beyonce or some other musician, you need to have all of that information in your database. This part is quite complex in order to be able to understand the application, and so we use an internal crowd for gathering this information. So this next slide is I want to walk you through how we do all of this. So there's an interaction between the device and our cloud, and it's a lot of times expressed in JSON files or XML files, such as the one that you see below. And we extract that information, and we have to transform it into a tabular form, and we put that into our Redshift database. Sometimes there's a need for us to decode something. For example, maps may appear in this coded manner, which requires some decoding. There's a couple of internal steps which I won't go into, and then we need to have the audio expressed. So each one of these is an utterance that's sitting in S3. And then we gather the information from our database. So it may look like something like this. So for example, here is the ASR text. What is the weather? Or get the forecast for Plano, Texas. And each one of these is expressed in terms of the action that the NLU took. So it's about the weather. It could be local, or it could be by naming a city. You could have a signal-to-noise ratio, which is in this next column, and then you have an audio length as well. And so with this now, you have all the information you need in order to do a transcription. So we'd send that information to the Crowdflower platform, and this is an example of what a conglomerated speech gathering effort would look like. So you allow the user to listen to the speech. You ask them if it's intelligible English or not. And then you ask if the audio is clipped. And if there's a need for transcription, they would express it here. And you ask whether there's background noise or not. In actuality, we do each one of these steps separately, but here we've conglomerated it in order to express the idea. Once we've done the transcription process, we're able to compute the word correct rate and the sentence correct rate. And at that point, we're ready to do semantic annotation. Semantic annotation looks something like this. So for example, you see the phrase, "Can you show me the nearest pharmacies?" In this case, it's a point of interest agent, and we're asking to find a nearby point of interest. And the criteria here is the POI, which is pharmacies. Now, an annotator can express this as being accurate, which in this case it is, or they can say it's inaccurate, and they may change the agent, the context, the command, or the criteria. And this is how the process evolves in terms of the work that the annotators do. Once we've done that, now we're ready to report everything. As I mentioned again, this is an in-production system, so we're sorry about the axes missing, but you can see that, we have a high level of accuracy for word correct rate and sentence correct rate for each of these agents. And then we also compute the NLU accuracy, or the end-to-end accuracy, for each of the agents as well. Lynn will go into more details about this. So with that, I'm going to hand this over to Lynn.
Hi, I'm Lynn Armstrong. I'm the developer that worked on our ETL pipelines and who evaluated Databricks. We had a few things we needed to make sure we could support with these new pipelines. We were going to be supporting more logs than we had ever had to process before with previous products. So we knew we had to have ability to scale. We had to provide analytics on the data. So we needed a method to extract different dimensions of the data so we could look at counts, latencies, status, or look for patterns in the data. We also had to provide end-to-end accuracy of our product. So we needed a way to collect all the data, measure how we're performing from end to end and internally in our system. We also had to provide data to our internal teams to help them improve their accuracy. So extracting particular pieces of data, frequency count, so they could make sure they're supporting what users are actually asking in production. The solution needed to be fully cloud-based. We didn't have resources to have any of this on site. The challenge with this is we had a very small development team, and at the time we were primarily using C# and SQL. Our legacy tools and data processing were all on site. Our team didn't have any operational resources, so if we were responsible for any hardware setup, software configuration, monitoring, or maintenance, we didn't have the staffing to do that. We also needed a solution in a short time frame. We chose Databricks and Spark to implement our pipelines. This was hosted in the cloud, and it was managed for us. We didn't need to purchase hardware or software. We didn't need to learn how to configure and set up Spark or clusters or learn how to do auto-scaling. All of this was built in with Databricks, so we had a quick jump start into getting development done in the Spark environment. Databricks came with developer account management, so it was easy to add support for users to share notebooks and to control permissions and access within our environment. As we were evaluating Databricks to see if we could use this for our pipelines, we were provided a technical resource. And since I was doing the evaluation and I had no experience with Spark or Scala, this was invaluable. If I would get stuck, I would have somebody to go to get help. Since all of our pipelines needed to be automated, we needed to schedule them to run at intervals, and this was also built into Databricks. So we didn't need to have various pieces of software to get the system up and running. Everything we could do within the Databricks environment. We could also alert for any failures with our scheduled jobs. So there we also had our monitoring capabilities built into the one environment. All of our data storage was on S3, our log files, our audio files, and we chose Redshift to store our data in tabular format. With Databricks, the integration with S3 was simple. We would mount our buckets with DBFS. There were Spark libraries to integrate with Redshift for reading and writing, as well as SQL, so we could get at our legacy data. We used Power BI for reporting already on site, so that was our logical choice for this new platform. Power BI supported reading data from SQL and Redshift. So here again are the components of our platform. And all of the work that we were doing was within Databricks and within the reporting system. So our first objective was to process millions of logs in an automated fashion. So the first pipeline that we built was a notebook to pull the data from Elasticsearch, run our transformations, and write it to Redshift. We chose to use Scala because there were so many examples available online. The notebook development environment helped with iterative development and exploration of the data. We were learning about the fields within our data, what we needed to extract for different pipelines for accuracy analysis or analytics. We used the Databricks scheduled job to automate the extractions. So here's a sample notebook where we're pulling data from Elasticsearch. And you can see that we're pulling it directly into a data frame. All the Elasticsearch configuration as far as the endpoint where we're pulling data from, the date range, the fields we wanted to extract, and our query are specified as an option. So for each service hosted in our platform, we were able to pull the logs. With each log, we had a unique request ID to associate requests between the logs. And we made sure we were extracting data that represented actual user requests in our platform. So this pipeline wasn't there to analyze debugging or informational logs, but actual production traffic. Each of the logs for each of the services was a different schema. Some were JSON, some were XML, some were a proprietary format. So this notebook had to do a lot of work to extract data fields and run transformations to get the data we needed. Some of the transformations need pieces of data from each log from different services. So we're able to easily join all of our logs to run that analysis. Lastly, we wrote our data to Redshift. Once the data was in Redshift, we had access to it from Power BI. And at this point, we could do all kinds of analysis on our data. The most basic analysis is how many requests are coming into the system, how many users are using the system. So we were able to see over time, by year, by quarter, by month, by week, by hour, what kind of traffic's coming into our system. This allowed us to see trends and to prepare our platform for load at different times of the day. We could also look at counts of requests per product to see which products have more or less traffic than others. We could also see counts of requests for features within the product. When I say features, I mean something like how many users are asking for an address. Maybe they want to navigate to an address. How many are asking to make phone calls with hands-free dialing? How many requests are looking for a POI, find the nearest Starbucks? Are there any nearby restaurants? Or maybe they're asking about the weather. So we could see in our product what things users were asking for with what frequency. All of our requests also had a status, a high-level status of how we did with the request. So we have a good overall view of what kind of traffic's coming into the system. And all the reports are filterable by date, by product. Other data we extracted from our logs was latency information. How long did the user have to wait for a response? So we have end-to-end user latency, and with all the other fields we extract, we can look at it from different angles, by product, by feature, by day, or by release of the platform. And within the end user latency, we can break it down to components within our system so we know which areas might need some tuning to perform faster. Another view that we like is to see the trend in growing traffic and that our latencies are not impacted. We don't want the platform to slow down just because we have more traffic. Within this log data, we can see what users are asking in the car. This data is very valuable for frequency analysis, recall scoring, and just understanding how the product is used. We had to make sure that the data was usable. Some of our data was encoded, and this isn't useful when we're looking at frequency analysis. And with that, we cannot score how our engine did. We need a plain text version. So we have additional pipelines that run after our initial data extraction to make the data more usable. So in some cases, we're decoding encoded data. In other cases, we're adding additional metadata. For example, we get a lat long for each request, but some of our analytics is based on region or market analysis, and they wanted to have access to a city or a state. So we provide reverse geocoding and add additional data into Redshift for analytics. We also split our data into training and test sets so that our teams can train with one set of data and test with another set of data and make sure that none of the requests belong to both sets. We provide additional analytics on the data that goes a little bit deeper. For example, we process audio files, and we write that metadata to the database. Some of the data we process for an audio file is the speech-to-noise ratio, the sample rate, the length of utterance, the length of speech within the utterance. All this information, this metadata, is written to Redshift to be available for reporting analytics. We also convert the audio to WAVE for our crowdsourcing pipelines. The audio that we have for the platform is all encrypted so that it's a smaller data size. This metadata can be used to analyze the length and frequency of requests that are happening in production. We can also look at the signal-to-noise ratio. Which vehicles have a quieter versus a noisier environment? Or overall products, what's the distribution of the noise of the requests? And this is useful because we want to train our models to match the noise environment that's in production. So if most of our environment is primarily low noise, that's what we'll train our system to be able to handle, with also a capability to handle some noisy as well. We have a pipeline also to measure the accuracy of our speech recognition. This pipeline needs to know what the user actually said in order to measure accuracy. As we mentioned, we use an external crowd to provide transcriptions for our audio. Then we need a method of scoring between our result from our speech recognition and the actual truth of what the user said. We use sentence correct rate and word correct rate to provide this measurement. When we measure, we use a normalized representation of the ASR result and the transcribed result. We use Crowdflower for our external crowd for collecting transcription information. This is just an example of a notebook which pulls results from our job in the crowd and verifies that we are getting 3 matching iterator agreements for a recording before we write that into our Redshift database as the truth of what the user said. We have another series of notebooks which pull the truth of what the user said, the result from our system, and normalize them. In some cases, the transcriber may use numbers numerically to represent numbers, or they may spell it out. When we're scoring our engine, we want to make sure that we're doing it in a normalized fashion. So first we normalize the text to represent numbers in the same manner. Once we have the score for the features of the product for our speech recognition engine, we can see how it's performing in production. The other measure we take is our natural language understanding. Are we acting upon the utterance in the way the user wants us to? So we have an internal crowd using an internal tool to mark the parts of speech for an utterance. This we compare against the results we got in production to see if we have an accurate result or not. Then we have a series of reports using the compared value of our annotated result from our internal crowd and our production result to see how accurate we were. When we're analyzing this data, we have a lot of dimensions and filters we can apply to evaluate the results. For example, these reports are all drill down. So if you want to analyze a particular feature of the product to see where we weren't performing well and where we can make improvements, you can drill through and look at the raw data. So we have access to the results from the platform and the results from the crowd, and where we got something wrong, we can listen to the audio and see which part of speech we got wrong and where we may need to add improvements to the system. This allows us in the end to know the user experience accuracy. How often did we actually give the right response to the user for what they said into the system? So again, this is able to be analyzed per product or per feature of the product. We can also group it by the noise level in the vehicle to see if we perform better or worse depending on the noise environment in the vehicle. We can also see for each user what their accuracy is with our product and group it per head unit or feature. In this case, for each product, the user accuracy median is well above 90% for all of our products, and 75% of our users are experiencing over 90% accuracy. Another important measure is what's our accuracy per release of the product. Our goal of this whole pipeline is to improve the accuracy of our product and improve the user experience. So since we're able to measure accuracy in production and all of our data is associated with the release, then we can do analytics on our accuracy per release and show that our accuracy is improving over time, which was the goal of the pipeline. As we built this pipeline, we learned a lot, and we encountered a few challenges. Initially with Elasticsearch, we discovered we had to match our Spark library Elasticsearch version exactly with the hosted endpoint. The JSON query syntax used in Elasticsearch can vary between ELK deployments, and your filters may appear to work because you don't get an error on your JSON syntax, but they may not actually work, and you won't get an error back in those cases. So we found that it was good to debug our queries in other third-party tools before plugging them into our notebooks. Since we were brand new to Spark and Scala, this was our largest learning curve. Trying to interpret error messages and discover the actual problem is a science in itself. Also trying to discover when the error occurred, because it's not until you're actually performing an action on your data that the code's executed. We tried to use the built-in JSON parsers and struggled quite a bit trying to handle some of the variations of our JSON logs. We ended up using a third-party library, but we did spend a bit of time struggling with the built-in parsers. In some cases, we needed to write data to a file. And as we wrote our data frames to a file, we discovered we don't actually write to a file. So that was another learning curve. We had to write our own solution to create a single CSV file representation of a set of data. We also tried using CSV files to share data between pipelines and trying to get the markup correct and delimiters correct and the schema of our data correct was error prone. We tried using Parquet, and that was very simple and very high performing, and so we use that for all data sharing between our pipelines now. We use Databricks scheduled jobs for all of our pipeline notebooks, and we were using the status message returned when exiting a notebook to indicate the notebook status. Later, we realized that won't actually fail your job. So if you want to trigger a failure on a notebook, you need to throw an exception. With Redshift coming from the SQL world, the biggest learning curve was the fact that their primary and foreign keys are not enforced. So if you want to control duplicates, you need to have methods to handle that yourself. Lastly, with Power BI, although they supported reading in data from Redshift, they didn't support automatic updates. So in order to keep our reporting analytics up to date, we had to manually update the reports until the feature was released. Okay, this takes me back to Pavin.
All right, can you all hear me? Very good. So in order to basically reveal how well we did with the Databricks Unified Platform and our CIP process, these are the improvements that we've gotten in just 3 months of using this system. The ASR word recognition rate has improved by 14%. The sentence recognition rate has improved by almost a quarter. The NLU has improved by over 3%, and the end-to-end accuracy that customers experience has improved by 16%. Our ability to efficiently build data pipelines in Databricks has reduced our overall development and maintenance periods, and our customer is quite satisfied with the results that we've gotten. We've also compared our ASR performance against the major speech providers' ASR, and because we are training our system based on the data that we're actually getting, our word recognition rate and our sentence recognition rate have surpassed what the major speech provider provides as well. This takes us to our conclusions. Thanks to Databricks and Spark, we've really overhauled how we do data processing at Voicebox. Our ETL and reportings have improved significantly, as have our processes, and we're able to deliver end customer enhancing ROIs, return on investment, to our customers. And we may eventually use the Databricks Unified Analytics Platform for our NLU modeling as well. We've faced challenges along the way, which we've dealt with, and we're working with Databricks to address any new ones that come up. And this is our information for, where you can find out more about Voicebox, or you can email me directly. And I think now we're ready for questions.
Well, Pavin, Lynn, hey, thank you for that excellent presentation. And we'll get started with today's Q&A. I want to thank the audience for their participation. We've had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Pavin and Lynn if you'd like to contact them following today's webinar. So let's get started. I must say, I am just overwhelmed by the complexity of the system that you all have had to develop to reach this level of performance, and I think the audience questions reflect the same thing. Can you simplify for us a little bit about what has been the biggest benefit of using Databricks in lieu of the manual system that you used before?
Sure. We covered this extensively in the presentation. We've improved our ROI metrics quite significantly since we've rolled out. Though we don't mention the customer name at their request and are presenting, what we're presenting is not a demo, it's actual production software. Thanks to CIP, which is enabled by the data team using Databricks, in just 3 months we've improved our customer satisfaction by 16%. So that's a significant uplift that we can talk about.
Well, Pavin, thank you for that answer. Now, you showed a lot of detail, and their audience members would like you to review some of the elements that you've shown us. Specifically, which databases are you using for SQL and for NoSQL, and what specific types of data are going in there? And this probably also relates to the audience question about how Databricks and Spark fit into your overall workflow.
The technology that we're using for data storage is Microsoft SQL Server. That was our legacy system. And for Redshift, we're using SQL. Queries, we're not using NoSQL.
Oh, not at all?
No.
Oh, okay. Well, thank you. Then can you explain again or review for us again how Spark and Databricks fits into your overall workflow?
Databricks notebooks are actually processing all of our workflow between databases, so between Elasticsearch and Redshift, between SQL and Redshift, between Redshift and SQL, between S3 and Redshift. So all of our workflow is going through Spark and Databricks.
Okay. Well, thank you for that clarification. I'm going to move us back here to this slide so that people can see your contact information. Lots of technical interest in the problems that you must have identified along the way. For example, audience would be interested to know what's the volume of the data captured by just 1 day of transcriptions from a car system that CAP is able to manage?
So that part I'll have to hedge a little bit because this is in production data and our customer is sensitive to this fact. But what I can share with you is that in the first 6 months we want to collect as many as 1 million transcriptions in order for the process to improve. So we're in the process of doing that. We're about halfway there.
Okay. And probably related to that question, the audience is interested to know if you take any active measures to reduce or control file sizes in order to control your AWS costs.
We're not doing any of that at this time, but we are going through a phase of development where we're going to change from processing everything and all data to using random sets of data, sample sets that are statistically significant.
Yeah, once we pass the 1 million transcription marker, then we're able to switch to just sampling the data. And that at that point, we don't need to acquire as much data as we have before.
I see. Okay, that makes perfect sense. From a data science standpoint, the part that seems to really interest the audience is if you could tell us a little bit about the deep learning models that you're using to train your sets.
Yeah, this is more a presentation about what we've done in the data team. We have a very active ASR and NLU teams, and they don't currently use Databricks. We have some legacy systems in-house. with GPUs that we use for deep learning. So they would be more of a proponent of giving additional information about that.
Okay, yeah, thank you.
We have a very sophisticated NLU system. I will say that.
I can only imagine. But then let's just talk about updating the criteria and the accuracy pipelines. That must be a major data effort. How often or to what extent do you end up updating those pipelines?
Typically, we update our criteria pipelines once a month because that's the cadence at which we are putting out new versions to our customer, and so that's typically the frequency. Of course, we update our systems more frequently than that. So for example, for the music, there's new songs and new artists every week, so we scrape that stuff every week.
That makes perfect sense. Lynn, in your part of the presentation, you mentioned something called a blind set, and the audience would like to know what that means.
Okay, that's something that was requested by our speech scientists. They wanted to hold some data off to the side that they don't know what the data is. They don't have access to that data. It's not part of their test set. It's not part of their training set, but it can be used if needed for any testing where they've never seen that data before. So it's kind of some data we hold off to the side that they don't know what it is and they don't get their hands on.
Well, that's something that we would all recognize as holdout data. Yep, completely understand. Makes perfect sense. Is there any caching happening to limit the inquiries to offload traffic to Redshift to speed up response time?
We are not doing any of that at this time, but as I mentioned in our second phase, we're definitely going to need to do some work to handle larger volumes. So that may be when we need to dive deeper into that.
Okay, well, thank you. I thought that one of the most interesting problems that you described was the issue of inaccuracy, where you have car noise and multiple people speaking, and the audience was interested to hear more about that.
What specifically did they want to know about that?
Well,
what I can mention is that that impacts the ASR system severely. If people are chit-chatting or there's noise and so on and so forth, and our NLU system is built in such a way that it can recover, even if the transcription is not perfect. We have 50% end-to-end accuracy, even in cases where our ASR gets one or two words wrong in a particular sentence.
Well, thank you. Thanks for that clarification. I tell you, I was particularly interested. I see that you use both external and internal active learning or human-in-the-loop reviewers. What percentage of your data do you end up passing by human-in-the-loop reviewers to ensure accuracy?
For transcriptions, we're currently sending all of the data through that pipeline. For annotations, we're sampling that, and about 10% of the data is currently going through that annotation process. We also have another step that we do because the crowd may be acting in ways that are not always beneficial to our improvement requirements. And so we use some of our internal annotators to do a verification of the crowd results as well.
Oh, interesting. Well, Pavin, Lynn, thank you for some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Pavin, Lynn, and the Voicebox team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for April 5th, that's our next DSC webinar, and that's the State of Data Preparation in 2018 to be presented by Trifacta. Also, remember that today's taping will be available on demand for viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Databricks for their sponsorship, and particularly to our speakers today, Pavin Kadena and Lynn Armstrong of Voicebox, for their insight into today's topic. So this is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on April 5th. Have a great day.
Thank you.